lower bound for the current upper bound. So in n log n steps, we can essentially identify all of the upper and lower bounds. Right, so my task was to implement this algorithm, and so a lot of it was very detail-oriented, going through individual portions which were omitted from the original paper and providing algorithms for how to achieve that part of the overall algorithm. So I won't go through each individual part. What I want to focus on instead is one particular area which was pretty interesting, which is the question of how exactly do we compute the strongest bound update? So we've just briefly seen the theta tree, and using the energy envelope, we can then find the set of tasks that must precede our current task. But as we saw at the beginning, we then need to look at the subsets of that set of tasks in order to get the strongest bound update. And in order to do that, we have to modify the way that we use the theta tree. Now, this is the most complicated part of theta tree edge finding. It's a little bit difficult to follow in the paper, partly because while there's an algorithm for how to do it and a proof that the algorithm is correct, there's no explanation for why it works or what it's actually doing. And when I attempted to implement it, I could not get it to work. So I had to investigate a little bit further. Essentially, to compute the strongest bound update with the theta tree, we need to do two things. One, we find the smallest task interval, which here I'll refer to as the smallest omega, which is a subset of our overall task set theta. So the smallest omega that has enough energy to interfere with the scheduling of our current task. Then we calculate the energy envelope a second time, but this time we force it to include all of the tasks that were in this set omega. So to give a quick example, here we have just a set of generic tasks where the set responsible for the energy envelope of the overall set is simply the rightmost two sets, so the max envelope set there. But for the current task that we're attempting to adjust bound of, we suppose that this set is not energetic enough to interfere with the scheduling of that set. Instead, we have a larger set, which I've labeled here min omega, which is the smallest task interval, which does have enough energy to interfere with the scheduling of the current task. And an even larger set than that, which I've labeled best omega, which is the one we actually want to find. That's the task interval that will give us the strongest update to the bound of the current task. So in order to find this, we first have to divide the theta tree into two subtrees, which I've labeled here alpha and beta, where the lower bound of the set min omega, so that again is the smallest sub-task interval which is energetic enough to interfere with the current task. The lower bound of that forms the rightmost node of the alpha subtree. Then if we take the energy envelope of the alpha subtree, that will be based on exactly the same lower bound as the lower bound that we're looking for, the lower bound of the best omega set. And then we can add the energy of all of the tasks in the beta subtree, and what we wind up with is the energy envelope of our best set. Unfortunately, none of this was actually explained in the paper. It was just given as an algorithm. So once I understood exactly what we were attempting to accomplish there, I was able to figure out what was wrong with the implementation, which was, first of all, the update section of the original paper had an incorrect definition and the proof wasn't right, which is part of the reason why it was such a confusing section. And secondly, the published algorithm had an incorrect formula in it, which was messing up all of the calculations. And along the way, I also noticed that actually cutting the theta tree is unnecessary. You can use the existing values in the tree to calculate both the energy envelope of alpha and the energy of beta. And you can do all of this in a single leaf-to-root traversal from the task that forms the lower bound of the min omega. There were also several other clarifications and corrections that I was able to provide to the original paper. I implemented a parallel version of the filter, which was kind of interesting. I combined this filtering algorithm with another filtering algorithm by the same author, which allows for variable durations of the individual tasks. I give a proof that this algorithm is monotonic, which is an important property for filtering algorithms in constraint programming, and several other specific areas. But, okay. Thank you very much.
Great, thank you very much. So we have time for a few questions, if there are any. So then I can ask.
Yeah. So, did you get in contact with the original inventor, and did he comment your findings?
Yes, of the two significant corrections, one had already been identified by someone else, although it hadn't been published yet, and I believe the other was novel. And now there's a corrected version of the original paper with both in it. Okay.
So have you done some experimental evaluation, how much faster the 60 node became after introducing this?
Not completely within 6 Prolog, no. It hasn't actually been, or the last time that I checked, it hasn't actually been moved in to the 6 internals. This was implemented as a standalone filter. But I did compare it against standard edge finding, and it was substantially faster. Yes.
No further questions? So then this concludes this session, and thank you very much. And now we're supposed to have the poster introductions, I think. Anders and Helge, will you take over?
We were just trying to find what
Oh, okay, so you know where to go tonight. That's good.
Would it be okay if we did this thing tomorrow morning? After,
No, I'm not tomorrow. Yes.